Okay, example 1. In the Pacific Ocean, 2 islands, 2 fictional islands, Ubba Dubba and Bubba Dubba. I'm going to call them AD and BD for short. On these islands, there are colonies of squawker birds, which I'll call SBs. In the year 2000, the squawker bird population on AD and BD could be modelled by these 2 models. And you'll note here, irrespective of what I just spoke to you about, these 2 models both have base 2.8, not base E. So if we're going to do some gradient calculations, we might transform that 2.8 to an e to the power of k, whatever that k is. 2.8 to the power of 0.3t and 2.8 to the power of 0.28t are the 2 populations respectively, and you can also see some initial values there as well. So with that in mind, at time equals 0, what was the initial population of Ubba Dubba AD? AD. 1200, BD was 1500. So you want me to use Ubba Dubba, Bubba Dubba? Okay. I think it's actually Ubba Dubba. I've got to get that right. I feel like this is an episode of the Flintstones. Okay. Ubba Dubba and Bubba Dubba. P is the population of squawker birds, and T is the time from the beginning of the year 2000 in years. What was the initial population of each colony? So we've just done that one. A, I'm not writing them down, by the way, 1200 and Ubba Dubba. I know you're just drawing it out of me. B, sketch a graph of both population models on it. So if you're going to ask to sketch a graph in an exam, I would like you to use a ruler, obviously, but there's no real requirement for it to be completely perfect. So this starts at 2000, builds up. The population of, I'll start with AD, is in red. The population of AD starts at 1200, so I might set 1200 here, and we'll have our scale going up to 1000 here. You'll notice here that if I've set 1000 as my second blue line, that's enough information for that scale. And the same here. So if you mark some points, you might just have 2010 here, for example, and that's enough information there. Now, the red one has a relative growth rate of, the bases are the same, but a relative growth rate of 0.3 compared to the one that is going to be blue here in a minute, which has a relative growth rate of 0.28. So the red one's growing not a lot quicker, but it is growing quicker. So we can expect that red one to arbitrarily do that, but the blue one starts higher here, it isn't growing quite as quick, and somewhere they meet. I'm going to stand outside. No, just joking. BD. There we go. Bubba Dubba. So that's my graph. Everybody happy with that graph? It's not perfect. You might have to denote some extra points to make it a little bit better, but ultimately, as long as you've got some element of scale and you've got those 2 lines and you've clearly shown that they intersect, one starts higher than the other and in the right order, then we're good. How many squawker birds are there on both islands after 10 years? So this is just a simple case of substituting 10 in. And so C, we get for Ubba Dubba, the population is equal to 1200, and I might need your help with the calculator here, times by 2.8 to the power of 0.6 times 10. BD 0.3 times 10, yes. .24. Is it really? Oh yeah, I suppose that's growing pretty quick. Okay. And this one's 0.28 times 10. And this will see if the populations have passed each other by the 10th year or not. So not quite. Ubba Dubba hasn't quite caught up to Bubba Dubba yet. A pretty good approximation, and that question's going to come. D, When does each population reach 100,000 birds? So in this case, for AD, we want the population to be 100,000. So we put 100,000 here, and that's equal to 1,200 times 2.8 power 0.3 T. Okay, hold on. Just a quick run through the rearrangement here. We get that divided by 1200 is equal to 2.8 power 0.3 T. We can simplify things a little bit, but I might just leave it as 1,000 over 12. And then we can rearrange this into our exponential form. 0.3 T is equal to log base 2.8 of 1,000 over 12. Hopefully remember that if you go into your math matrix screen, the main calculating screen on your calculator, and press the math button, which is F4, there's a log AB on there. That's where you can get in and just do your quick log 2.8 of that stuff. And T will be equal to that divided by 0.3. 10 was about 26,000. It's tripling each 10 years. No, 2.8 to the power of 0.3, whatever that is, that's the growth rate. So I'm expecting it to be maybe 12 or 13 years. 2 years. So that's 2014 based on, so this is a when question. So this is about 2014. Sometime in the year 2014, maybe March 2014. And BD, can you do BD for me? If I rearrange it for you, 0.28 P is equal to log base 2.8 of 100,000, and this time it's over 15. I could simplify that more, but 15 divided by 0.28. And so that's also 2014, but a little bit later. So it looks to me like at that stage, BD has been surpassed by AD. So when we get on to question E now, in what year? Oh, actually, no, question E is slightly different. I'll talk about that in a second. If we were asked to find this point here, we would know it's somewhere between 2010 and 2015, but I don't know where we could find it. Probably 2012, 2013 sometime. But question E actually asks us, in what year will there first be 2 times as many squawker birds on AD as there are on BD? So that's the question. We want to know, and I'll do what you have on the side here. When does the population of AD equal the population of BD, but we want 2 times, no, hold on, the population of first be 2 times as many squawker birds on AD. So we want the population of AD to be 2 times BD. Is everybody happy with that first setup there? Just be careful the way you read it, because the question says, and I almost got it right, what year will there be first be 2 times as many squawker birds on AD as there are on BD? So we want the population of AD to be 2 times as many as BD. So you've got to get that 2 in the right spot. Once you've got that, then we can put our functions in. So AD was, am I right in thinking it was 1200? Yep. So we want 1200 times 0.8 to the power of 0.3 T to be equal to 2 times 1500 times by 2.8 power of 0.28 T. So now we've built that function. If we've got, and this is where you might have to change the base as well. If we've got 2.8 as our 2 bases, this question is relatively easy. And I'm going to show you a method that you'll almost certainly see in one of your exams and have to apply. But if the 2.8s aren't the same, if you haven't got the same bases, you will need to change one of them so you've got the same bases. Otherwise, you can't unless you use technology. The question may allow you to use technology. If you're allowed to use technology, you have your equation solver, or you can sketch the 2 graphs and find the intercepts, or you can use the solve n, which is the numerical solve button in the math matrix screen. And I'm about to run out of time, so I'm going to do this. 1200, actually I'm going to do it the other way around. 1200 times 2.8 0.3t over 2.8, 0.28t is equal to 3,000. And Alzani, I'm going to need your help here again. Because they're the same base, I subtract the powers when I divide. So I get 2.8 to the power 0.t is equal to 3,000 over 1,200. I know that 3,000 over 1,200 is 2.5. So I'm going to rearrange this into log form quite quickly. Log base 2.8 of 2.5. And then t will be equal to that answer divided by 0.02. This is from the year 2000, so that's in 2044 and a half. Probably I should get my answers here and put them into months, but I'll leave it at that for now. Hopefully that helps.